Ancient photons from galaxies formed 13 billion years ago are reaching us at this very moment. Scientists using advanced space telescopes have recently confirmed discoveries that challenge fundamental assumptions about how our universe developed. These observations reveal cosmic structures existing in places and times where theoretical models suggested they shouldn't be possible, forcing astronomers to reconsider what we understand about the scale and timeline of everything around us. Throughout this exploration, we'll travel to distances so extreme that conventional measurements become almost meaningless. We'll observe galaxies moving apart at velocities exceeding the speed of light, witness massive structures spanning incredible distances, and encounter empty regions of space larger than anything imaginable. Understanding the genuine magnitude of reality requires examining evidence that pushes the boundaries of human comprehension. Recent deep sky observations captured something remarkable. Scientists pointed their instruments at a tiny section of sky, no larger than what a grain of sand would obscure if held at arm's length. During 12 hours of data collection, light particles arrived from distant sources. When researchers analyzed the results, they needed to verify their count multiple times. Over 45,000 separate galaxy systems appeared within that minuscule viewing window. Each represents a complete cosmic island containing hundreds of billions of stars, spinning through the void of space. Each one exists in a portion of sky so small that looking upward on any clear night, you'd never notice that specific area. This extraordinary concentration defied predictions based on previous theoretical frameworks. Earlier computational models anticipated much sparser distribution of galaxies at extreme distances. New observations demonstrated the opposite reality. Wherever instruments point, countless galaxies fill the field of view. Consider what these numbers mean in practical terms. On the clearest possible night, standing far from urban light pollution, approximately 3,000 individual stars become visible to unaided human eyes. Now understand that every single galaxy in these recent images contains more stars than anyone could ever see without technological assistance. Multiply those 3,000 visible points by billions to comprehend one galaxy's stellar population. Then multiply that single galaxy by 45,000, all existing within one grain-sized patch of sky. The mathematics become overwhelming. If this concentration remains consistent across the entire celestial sphere, our observable universe contains far more galaxies than earlier estimates suggested. Previous calculations indicated perhaps 200 billion galaxies existed. Current evidence hints at 2 trillion, possibly more. Every direction we examine explodes with organized structure. However, counting galaxies alone doesn't reveal the complete story. These stellar systems exist at varying distances, representing different cosmic epochs. Light from nearby examples traveled millions of years before reaching detection instruments. Light from the most distant examples journeyed over 13 billion years. Observations capture multiple layers of cosmic history stacked within single images, like examining growth rings in ancient trees. Each galaxy represents a different period, a separate chapter in universal evolution. The deeper implications simultaneously terrify and excite researchers. If 45,000 galaxies hide within one randomly selected patch, what exists in areas not yet examined? Space telescopes cannot look everywhere simultaneously. Scientists must choose observation targets carefully, balancing research objectives against limited available time. Most of the sky remains unexplored at this resolution level. What lurks in those unexamined corners? These implications extend beyond simple enumeration. Galaxy density affects our understanding of dark matter distribution throughout space. It influences calculations regarding cosmic expansion rates. It forces reconsideration of how quickly structure formed following the universe's beginning. A cosmos this densely populated with galaxies demands more matter, more gravitational attraction, more dark energy to simultaneously hold everything together while pushing it apart. Scientists anticipated finding a cosmic web pattern, with filaments of galaxies threading through empty voids. Latest observations confirmed the web exists, but the connecting threads appear thicker than anyone predicted. The voids between them might be smaller and less empty than assumed. Previous models proposed vast expanses of nothingness punctuated by rare islands of matter. Reality shows something denser, more intricate, more interconnected than theoretical frameworks suggested. This discovery matters significantly for searching for life beyond Earth. More galaxies mean more stars mean more planets. More planets mean more opportunities for chemistry to accidentally produce biology. The odds of discovering another civilization improve with every galaxy added to the census. We thought we inhabited a universe with hundreds of billions of opportunities. Current observations suggest trillions exist. Yet here's the unexpected twist that keeps astronomers awake. Most of these galaxies remain unreachable. The universe expands continuously. Space itself stretches between us and them. Light from the most distant galaxies already shifts toward infrared wavelengths. Eventually, they'll fade beyond any telescope's detection capability. We see them now only because we built advanced instruments at exactly the right moment in cosmic history. Miss this observation window, and future civilizations might never know these galaxies existed. Initial deep field images revealed more than just density, they revealed urgency. The universe displays its full scale right now, today, before expansion carries too much of it beyond our observation horizon. What we discover during the next decade might represent our last chance to witness the complete cosmic inventory, and we've only examined one grain of sand worth of sky. One particular galaxy shouldn't exist according to current models. Scientists found it within the same deep field survey. It appears as a smudge of ancient light older than anything previously confirmed. Spectroscopic analysis revealed its secret. Light from this galaxy began traveling toward us 13,400 million years ago. It formed just 290 million years after the universe began. That time frame contradicts our theoretical models. Early universe conditions were supposedly too chaotic for galaxy formation. Hydrogen and helium dominated everything, still cooling from the initial explosive expansion. Stars had barely begun igniting. Dark matter had only started clumping together, pulling ordinary matter into gravitational wells. Galaxies should have required longer, needed more time to organize themselves into coherent structures. This galaxy didn't wait. The galaxy spans 1600 light years across, compact compared to modern spiral galaxies. But within that small volume, stars already burned brightly. Not just a handful of protostars, but enough stellar furnaces to make the galaxy visible across 93% of cosmic history. The light we detect now appears faint, shifted into wavelengths previous instruments couldn't observe. Advanced infrared sensors caught what no earlier equipment could detect. Here's why this discovery matters fundamentally. Every cosmological model depends on assumptions about when structure formed. Computer simulations start with conditions moments after the universe's beginning, then run forward in time. They predict when first stars should appear, when those stars should cluster into galaxies, when galaxies should merge into larger systems. This early galaxy formed earlier than any simulation suggested possible. Either our simulations contain errors or something accelerated galaxy formation beyond current understanding. One theory proposes dark matter concentrated faster than expected. If dark matter clumped into dense halos earlier than calculated, ordinary matter could follow more quickly, pulled by gravity into collapsing clouds that ignited stars. Another theory suggests the first stars were far more massive than we calculated, burning brighter and dying faster, enriching their surroundings with heavy elements that enabled rapid galaxy growth. Both theories remain unproven. What scientists know for certain is this galaxy exists. Spectroscopic data confirms its distance. The redshift measurement is solid, verified multiple times by different research teams. You cannot fake a redshift measurement. Light doesn't lie about how far it traveled or how much space expanded during its journey. The galaxy's chemical composition adds another mystery. Oxygen appears in the spectrum, an element forged inside stars and expelled when those stars died. But how many stellar generations does oxygen require? First stars contained only hydrogen and helium from the universe's beginning. When they exploded, they scattered heavier elements. Second generation stars incorporated those elements, created more, died, and scattered them again. Third generation stars inherited an even richer chemical mixture. This early galaxy shows oxygen just 290 million years after creation. The timeline feels compressed and rushed. Stellar evolution operates on schedules we thought we understood clearly. Massive stars live only millions of years before going supernova. Medium stars like our Sun last billions of years. To observe oxygen this early, multiple generations of massive stars must have lived and died in rapid succession. The galaxy needed time to build structure. Stars needed time to burn their fuel. Supernovae needed time to scatter their elements across space. 290 million years seems impossibly short. Yet there it sits, frozen in observational data, defying comfortable assumptions about cosmic timelines. Astronomers call this a tension between observation and theory. When reality contradicts your model, reality always wins. The model must change to accommodate new evidence. Finding this impossibly early galaxy also raises uncomfortable questions. If advanced instruments detected one galaxy that breaks the rules in a small survey patch, how many more exist beyond our current search areas? The telescope cannot examine the entire sky at the sensitivity required to spot these faint distant objects. It must prioritize targets, spending hours or days on single fields of view. Most of the universe remains unexplored at the depth required to spot these cosmic rule breakers. Each new deep field observation might reveal more structures that challenge existing theories. The implications ripple outward through cosmology. If galaxies formed faster than predicted, the entire timeline of cosmic evolution shifts earlier. Reionization, the period when first stars ionized hydrogen throughout space, might have happened sooner than calculated. The cosmic dark ages, the gap between the universe's beginning and first light, might have been shorter than theoretical models suggest. Everything we thought we knew about the universe's childhood is changing. And this early galaxy represents just the beginning of discoveries that challenge conventional wisdom. Imagine watching something that already finished billions of years before Earth formed. That happens every time advanced telescopes image a distant galaxy. Light entering the telescope left its source when the universe was young, then crossed space for eons. It traveled through expanding cosmos, through clouds of gas, past billions of other galaxies, until finally reaching our instruments on Earth. Light moves at 186,000 miles per second. Nothing travels faster through space. That speed limit defines how we experience the universe. When you see lightning, you watch photons that left the electrical discharge milliseconds ago. When you see the moon, you observe light from 1 second in the past. When you see our closest stellar neighbor, you watch light from over 4 years ago. Scale that principle up to cosmic distances. The Andromeda galaxy sits 2.5 million light-years away. Every photon from Andromeda began its journey toward Earth when our ancestors were barely learning to walk upright. The light shows us Andromeda as it was, not as it is currently. If that galaxy exploded yesterday, we wouldn't know for another 2.5 million years. Advanced space telescopes look farther still. They detect galaxies whose light traveled 13 billion years or more. When those photons started their journey, Earth didn't exist yet. Our solar system didn't exist. The Milky Way was still assembling from smaller proto-galaxies. Dinosaurs wouldn't appear for another 12 billion years. Understanding this temporal displacement changes everything about measuring the universe. Astronomers don't measure distance directly. They measure time. When we say a galaxy is 13 billion light-years away, we mean light from that galaxy took 13 billion years to reach us. But here's the complication that makes cosmology challenging. Space expanded during that journey. The galaxy moved while light traveled toward us. Imagine running on a treadmill that constantly speeds up. You run forward at steady pace, but the treadmill pulls the finish line farther away faster than you approach it. Light faces the same problem crossing cosmic distances. As photons cross space, space itself stretches, carrying distant galaxies farther from us. This means the galaxy we observe isn't where it was when light departed. When light left this early galaxy 13.4 billion years ago, that galaxy was much closer. Perhaps 3 billion light-years away. But during the journey of its light toward us, space expanded continuously. The galaxy receded, carried by cosmic expansion. By now that galaxy sits over 30 billion light-years distant. We see its past position, not its present location. This creates a strange disconnect between observation and reality. Every distant object telescope's image exists simultaneously in two places conceptually, where we see it in the past, and where it actually is now. We can calculate the current position using expansion rates, but we can never observe it in its present state. Light from the galaxy's current state hasn't reached us yet. It will arrive billions of years from now. The travel time also affects how we understand galaxy evolution. We see this early galaxy as it was 290 million years after the universe began. But that galaxy kept evolving after light left its location. It might have merged with neighboring galaxies. It might have grown into a massive elliptical system. It might have died, with stars exhausted and gas depleted. We'll never know what happened next in its story. The light from 1 billion years later is still in transit, crossing space at its steady pace. Light from 2 billion years later hasn't reached halfway to us yet. Every subsequent chapter in that galaxy's story remains hidden, encoded in photons that haven't yet completed their journey toward Earth. This is the price of looking deep into space. We see history, not the present. We see beginnings, not endings. We watch the universe's childhood while the universe has already grown into something unrecognizable. The galaxies we study might not even exist anymore in any form we would recognize. But here's what keeps astronomers searching despite these limitations. Even though we see the past, that past is real. Those galaxies existed. Those stars burned. Those atoms assembled into complex structures. By studying light from different distances and different eras, we piece together the universe's biography. We see infant galaxies at 13 billion years ago, Adolescent galaxies at 8 billion years ago, mature galaxies at 3 billion years ago. We watch the universe grow up, and every photon that crosses space carries information we cannot obtain any other way. The numbers sound impossible at first glance. If light traveled for 13 billion years to reach us, the galaxy should be 13 billion light years away. Simple mathematics, except space doesn't hold still while light travels. Space expands, stretches, grows larger with every passing moment. That expansion changes everything about distance calculations. When light left the most distant galaxies current telescopes observe, space was smaller, much smaller than today. The universe was perhaps 1/10 its current size. Galaxies sat closer together. The distance light needed to cross was shorter than it appears now. But as those photons traveled toward us, space expanded beneath them continuously. Think of an ant walking across a stretching rubber band. The ant moves forward at steady speed, but someone keeps pulling the rubber band longer. The ant advances, but the far end of the band recedes faster than the ant walks. By the time the ant reaches the end, the band has stretched far beyond its original length. Light experiences this same phenomenon crossing cosmic distances. Photons from distant galaxies move toward us at light speed, never slowing, never stopping. But space expands while they travel. The expansion doesn't slow the photons down. Instead, it increases the total distance they must cover. By the time those photons reach advanced telescope mirrors, the galaxy they left has moved much farther away. Current calculations place the most distant confirmed galaxies at over 30 billion light years from Earth right now. Not 13 billion, but 30 billion. That galaxy we see from 13 billion years ago currently sits 30 billion light years away because space expanded during the light's journey. If we could freeze time and measure the distance directly, we would need to cross 30 billion light years of space to reach that galaxy's present location. This creates the observable universe's true scale. We can see in every direction roughly 13,800,000,000 light years back in time. That's the age of the universe. The maximum time light has had to travel since the universe became transparent to radiation. But those galaxies we see at the edge have all moved farther away due to continuous expansion. Looking in all directions, the observable universe spans roughly 93 billion light years across, 93 billion light years from edge to edge. Earth sits near the center of our observable bubble, not because we're special or in a privileged location, but because observation defines the sphere. Any observer, anywhere in the universe sees themselves at the center of their own observable region. Each location has its own cosmic horizon, its own sphere of visibility. But here's what disturbs comfortable thinking about cosmic scale. The 93 billion light year sphere represents only what we can see from our location. The actual universe extends beyond that observable boundary. How far beyond? Nobody knows for certain. It might be infinite. Current measurements suggest space is flat, which typically implies infinite extent. If true, the universe has no edge, no boundary, no center point. What we observe is a bubble of visibility inside something vastly larger, possibly limitless. Imagine standing in thick fog. You can see perhaps 100 feet in any direction. That creates your visible sphere, 200 feet across. But the forest extends miles beyond the fog. You just cannot see it. The fog limits your observation, not the forest's actual size. Cosmic expansion creates a similar limit on what we can observe. Beyond a certain distance, galaxies recede faster than light can cross the expanding space between us. Their light will never reach us, no matter how long we wait. Those regions exist, contain galaxies, stars, planets, but they remain forever beyond our cosmic horizon. Advanced telescopes see nearly to that horizon. They detect galaxies from when the universe was just a few 100 million years old. Much earlier than that, the universe was too hot and dense for light to travel freely. Photons scattered off free electrons in a thick plasma. No galaxy images exist from before that era because photons couldn't escape the dense early universe. That earliest visible moment defines our ultimate look-back limit. We can observe the cosmic microwave background from 380,000 years after the universe began. Before that, the universe was opaque to radiation. Anything that happened in the first 380,000 years remains hidden behind an impenetrable wall of plasma. What advanced observations revealed is this: the visible universe is enormous beyond human comprehension, spanning 93 billion light-years. Yet even that unimaginable scale might represent only a tiny fraction of what actually exists. Most of reality hides beyond our cosmic horizon. We see a bubble. The universe is possibly infinite, and we have no way to observe what lies outside our sphere of visibility. After the universe began came expansion, cooling, the formation of first atoms, then nothing visible. Hundreds of millions of years passed in near total blackness. No stars burned, no galaxies shone, just hydrogen and helium drifting through expanding space, gradually pulled together by dark matter's invisible gravity. Scientists called this period the cosmic dark ages. Calculations suggested the darkness lasted until perhaps 600 million years after creation. Then first stars would ignite, galaxies would form, light would return to the cosmos. Advanced telescopes aimed at this era, expecting to find the universe just beginning to wake up. Instead, they found galaxies already assembled. Spectroscopic analysis confirmed structures formed as early as 200 million years after the beginning. By 500 million years, fully formed galaxies filled observable space. These weren't scattered proto-stars or loose collections of gas. They were organized systems with rotation, structure, defined shapes. The speed of assembly shocked researchers. Galaxy formation requires multiple steps, each taking time. Dark matter must clump into halos. Ordinary matter must fall into those halos. Gas must collapse, heat up, cool down. Molecular clouds must fragment. Stars must ignite. Those stars must create heavy elements through fusion. New generations must form from enriched material. Each step was supposed to require millions of years. Yet here were galaxies complete in just 500 million years total. The timeline compressed impossibly. Computer simulations couldn't reproduce this rapid formation without changing fundamental assumptions about physics, dark matter behavior, or initial conditions. One explanation suggests dark matter concentrated faster than models predicted. If dark matter halos formed earlier and denser, they could pull ordinary matter together more quickly. Stronger gravity means faster collapse. Faster collapse means quicker star formation. But this requires adjusting how we understand dark matter's properties, making it clump more efficiently than current theories allow. Another possibility involves the first stars themselves. Population 3 stars. The initial generation might have been far more massive than calculated. If these stellar giants burned hundreds of times brighter than modern stars, they could have ionized surrounding gas more effectively. Their deaths as supernovae would scatter heavy elements faster. This could accelerate subsequent generations of star formation. Both ideas remain hypothetical. What cannot be disputed is the galaxies exist. Observational data is clear. Spectra show redshifts corresponding to 500 million years after the beginning. Morphology shows organized structure. Chemical analysis shows evolved stellar populations. These discoveries force a confrontation with comfortable assumptions about cosmic development. Standard cosmology depicts a leisurely progression from chaos to order. The universe begins explosively. Space expands and cools. First atoms form at 380,000 years. Dark ages last until 600 million years. First stars ignite. Galaxies slowly assemble over the next several billion years. Advanced observations suggest a different story. The universe organized faster than expected. Within 500 million years of creation, galaxies already dominated observable space. The cosmic dark ages were shorter, the dawn brighter and more sudden. Instead of gradual awakening, the universe experienced rapid transformation from darkness to light. This matters for understanding everything that came after. If galaxies formed quickly, they had more time to evolve, merge, grow. The structures we see today might have deeper histories than we suspected. Galaxy clusters could be older. Superclusters could have assembled earlier. The cosmic web could have matured faster than theoretical models suggested. The implications extend to reionization. This period, when stellar radiation ionized hydrogen throughout space, supposedly lasted hundreds of millions of years. If galaxies formed earlier and more abundantly, reionization could have completed faster. The universe might have cleared its fog of neutral hydrogen sooner than models suggest. Every adjustment cascades through cosmic timelines. Change when galaxies form and you change when galaxy clusters form. Change cluster formation and you change when superclusters emerge. Change supercluster emergence and you change how the cosmic web evolved. Each discovery from advanced telescopes pulls on threads that unravel entire tapestries of cosmological understanding. Yet despite these challenges to existing models, astronomers feel excitement rather than frustration. Wrong models can be fixed. Incorrect assumptions can be revised. What matters is matching theory to observation, not defending outdated ideas. Advanced observations provide evidence. Scientists must now build better theories that explain rapid galaxy formation while maintaining consistency with other established facts. The work continues, accelerated by each new deep field image. But one question haunts every meeting, every paper, every discussion. If galaxies formed this quickly 500 million years after the beginning, what happened even earlier that we haven't detected yet? The shapes made astronomers double-check their instruments. Advanced observations revealed not just early galaxies but mature ones, complete with spiral arms, central bulges, defined structures. These features supposedly required billions of years to develop, yet there they sat, already formed less than 1 billion years after creation. Spiral galaxies are delicate structures. Arms wind through disks of stars and gas, shaped by density waves and gravitational interactions. Building this architecture requires time for rotation to organize matter, for dark matter halos to stabilize, for stellar feedback to regulate star formation. Current models suggested spirals didn't appear until at least 3 billion years after the beginning. Advanced telescopes found spirals at 700 million years. The images left no room for interpretation. Clear spiral structure. Multiple arms, central concentration. These weren't irregular blobs of stars slowly organizing. They were already mature systems with rotation curves, organized stellar populations, distinct morphology. Elliptical galaxies raised similar questions. These massive smooth systems form through galaxy mergers. Two or more spirals collide, their collisions ejecting gas and leaving behind a ball of stars. The process is violent, chaotic, requiring multiple merger events to build large ellipticals. Scientists expected ellipticals to appear late in cosmic history after billions of years of galaxy interactions. Advanced observations found massive ellipticals already assembled before the universe was 1 billion years old. The size posed its own mystery. Some of these early ellipticals contained stellar masses equivalent to 100 billion stars, similar to our Sun. Where did all that matter come from? How did it concentrate so quickly? Gas clouds in the early universe were hot, turbulent, difficult to collapse into dense stellar factories, yet collapse they did. Chemical composition added another layer of strangeness. Mature galaxies show chemical enrichment with heavy elements created by multiple stellar generations. The spectra from these early mature galaxies revealed oxygen, carbon, nitrogen, elements that require stars to live and die, spreading their processed material. This demands time. Massive stars live only a few million years before exploding. Medium stars last billions of years. To achieve the chemical enrichment detected, several generations of massive stars must have cycled through birth, life, death. That should have taken hundreds of millions of years minimum. These galaxies accomplished it faster. One controversial explanation suggests the first stars were far stranger than modern ones. If population 3 stars burned at extreme masses, perhaps hundreds of times larger than anything we see today, they could have lived and died in just thousands of years. Thousands, not millions. Rapid cycling would scatter elements quickly. But this requires stellar physics unlike anything observed. No confirmed population 3 star has ever been directly detected. We infer their existence from chemical signatures in ancient gas clouds. Making them massive enough to explain observations pushes them into speculative territory. Another idea proposes accelerated star formation. If early galaxies converted gas into stars far more efficiently than modern galaxies, they could build large stellar populations quickly. Modern galaxies convert only a small percentage of available gas into stars. Maybe early galaxies operated differently, turning 50% or more of their gas into stars in rapid bursts. Both theories face challenges. Star formation too efficient creates different problems. It would deplete gas reserves quickly, shutting down future star formation. Yet many of these early mature galaxies show ongoing star formation, suggesting they retained gas despite earlier bursts. The balance proves tricky to model. The mature morphologies also suggest stable conditions. Spiral arms don't persist in chaotic environments. They get disrupted by mergers, torn apart by gravitational interactions. Their presence indicates the galaxy has settled, found equilibrium, stopped experiencing major disturbances. That stability supposedly required billions of years in a crowded early universe where galaxies constantly collided. Somehow these systems found calm in the chaos. What disturbs cosmologists most is not one mature galaxy appearing early. It's the abundance. Deep field surveys reveal dozens of mature systems in small patches of sky. If this density holds across the entire universe, mature galaxies dominated within the first billion years. The universe skipped childhood and jumped straight into adolescence. This accelerated maturity affects predictions about galaxy evolution. If maturity came early, what happened during the next 12 billion years? Did these galaxies continue evolving, or did they plateau? Modern galaxies show diverse properties, but maybe that diversity was already established early and simply persisted. We thought galaxy evolution was progressive, developmental. Advanced observations suggest it might have been rapid and early with less subsequent change than assumed. The universe assembled its structures quickly, then spent billions of years in relatively stable configurations. If true, this reshapes our entire narrative of cosmic development, and it makes the next question unavoidable. What physical processes operated in the early universe that no longer function today? Space isn't randomly filled with galaxies. They organize into structures, vast patterns threading through the void. Astronomers call this the cosmic web, filaments of galaxies connected by gravity surrounding enormous empty regions. Previous observations revealed hints of this web structure. Advanced telescopes confirmed it extends far deeper into cosmic history than anyone mapped before. The web began forming early. At just 2 billion years after the beginning, observations detected filamentary structures stretching across tens of millions of light years. Galaxies lined up along invisible threads of dark matter, creating a pattern that resembles neural networks or fungal mycelium. The similarity isn't coincidence. Gravity follows mathematical rules that create similar structures across scales. Dark matter clumped first, forming the skeleton. Ordinary matter followed, pulled into the gravitational wells created by dark matter concentrations. Where filaments intersect, matter piles up densely. These intersections become galaxy clusters, the nodes of the cosmic web. Between filaments lie voids, enormous regions of space where few galaxies exist, where matter was pulled away toward denser regions. The voids aren't completely empty, but contain far fewer galaxies than average. Some voids stretch across hundreds of millions of light years, vast bubbles in the cosmic foam. Advanced instruments traced individual filaments across previously invisible distances. One structure spans over 300 million light years, connecting multiple galaxy clusters in a continuous chain. The filament contains thousands of galaxies, all moving under the influence of collective gravity. Gas streams along these filaments, funneling material from low-density regions toward high-density nodes. This flow feeds galaxy growth. Galaxies at filament nodes receive constant infall of fresh gas, fuel for ongoing star formation. Isolated galaxies far from filaments exhaust their gas reserves and go quiet. The cosmic web doesn't just organize galaxies spatially. It determines which galaxies thrive and which starve. Previous surveys mapped the local cosmic web within a few billion light years. Advanced telescopes extended the map to 10 billion light years, showing the web existed and functioned much earlier than expected. This early establishment means the large-scale structure of the universe was set quickly, perhaps within the first 2 billion years after creation. Once established, the pattern persisted. Filaments grew thicker as more galaxies fell into them. Voids grew larger as expansion pushed them apart, but the basic topology remained consistent. The web we see today is the same web that formed billions of years ago, grown and expanded, but fundamentally unchanged. This stability has implications for dark matter. If the web formed early and persisted, dark matter's distribution must have been stable. Dark matter cannot evaporate or disperse easily. It concentrates in filaments and clusters, holding the structure together despite cosmic expansion. Without dark matter, the web would dissolve as expansion pulls galaxies apart. The web also influences galaxy properties in unexpected ways. Galaxies along filaments tend to be spiral, actively forming stars. Galaxies at cluster nodes tend to be elliptical, older, quieter. Environment shapes evolution. Your location in the cosmic web determines your future. Advanced observations revealed something else strange about the web. Some filaments appear thicker, denser than cosmological simulations predicted. If simulations are accurate, this suggests additional matter exists in filaments that we haven't detected. The missing mass might be dark matter, or it might be ordinary matter in forms too faint to see directly. Warm gas filling the space between galaxies could account for some of this. This intergalactic medium glows faintly in X-rays, visible only with specialized instruments. Advanced telescopes cannot detect it directly, but the gravitational effects suggest its presence. If confirmed, this gas represents a significant fraction of the universe's ordinary matter, previously uncounted. The cosmic web also sets the stage for everything that follows. Galaxy collisions happen when filaments intersect. Supercluster formation occurs at major nodes. The distribution of matter at the largest scales determines where structure concentrates. Understanding the web means understanding the framework within which all cosmic evolution occurs. Yet the web itself poses mysteries. Why did it form this particular pattern? Initial conditions after the beginning were nearly uniform, with only tiny fluctuations in density that later grew into structure. But how did those tiny quantum fluctuations during the earliest moments create a web pattern billions of light years across? The connection between quantum and cosmic scales remains poorly understood. Inflation theory suggests quantum uncertainty during the universe's first fraction of a second got stretched to cosmic size. Those stretched uncertainties became density variations. Gravity amplified the variations into the web. But the precise mechanism linking quantum foam to galactic filaments involves physics we cannot test experimentally. Advanced observations cannot answer that question directly. But by mapping the web across cosmic time, they provide data that theorists use to test inflation models. The web's structure constrains what could have happened during inflation. Too much variation or too little both cause problems. What we observe must match what inflation predicts, and increasingly small mismatches appear between observation and prediction. One massive structure hangs in space like a cosmic monument to gravity's power. This galaxy cluster sits 7 billion light-years away, the most massive cluster ever detected at that distance. Mass equivalent to 3 quadrillion times our Sun crushes together into a relatively small region. The gravity is so intense it bends space, creating gravitational lensing visible in every observation of the structure. But this cluster isn't alone. It sits within a larger structure, a supercluster that extends over 1 billion light-years. Superclusters are collections of galaxy clusters, the largest gravitationally bound structures in the universe. They represent the ultimate scale of cosmic organization. 1 billion light-years travel at light speed, and you would need 1 billion years to cross it. The entire history of complex life on Earth from first cells to humans spans less time than crossing this single structure. Every species that ever lived, every ocean that ever formed, every mountain that ever rose, all of it happened in less time than light needs to traverse this supercluster. Yet this supercluster isn't even the largest. Other superclusters measure between 500 and 650 million light-years across. Some claim structures span 10 billion light-years, though their status as single-bound structures remains debated. These structures challenge our understanding of cosmic formation timelines. Building something a billion light-years across requires gravity to pull matter together across vast distances. But cosmic expansion fights against gravity. Space grows larger, pushing structures apart. For a supercluster to form, gravity must overcome expansion, concentrating matter despite the universe pulling everything apart. This takes time. Current models suggest superclusters need at least 8 billion years to assemble. Matter must flow from surrounding regions toward the densest spots. Galaxy clusters form first. Then those clusters gradually attract each other, creating larger associations. Yet this massive cluster already existed 7 billion years ago. Light from it took 7 billion years to reach us. When that light left, the universe was only about 6,800 million years old. By that time, this cluster had already assembled into a massive structure, and joined a supercluster formation spanning 1 billion light-years. The formation timeline feels compressed again. From the beginning to this cluster's existence required less than 7 billion years, half the universe's current age. Somehow, gravity organized matter into billion light-year structures in just half the time available. This cluster itself shows signs of ongoing assembly. The cluster is actually two massive clusters colliding at several million miles per hour. The collision generates shock waves, heating gas to hundreds of millions of degrees. X-ray observations reveal the hot gas glowing intensely. The collision will eventually merge both clusters into one even more massive structure. This process takes billions of years. The clusters approach, interpenetrate, separate, return, merge. Gas collides and heats. Galaxies pass through each other, mostly untouched because stars are so far apart. Dark matter halos overlap, combining gravitational influence. Eventually, everything settles into a new equilibrium. We see one moment in this long dance. The collision happened billions of years ago, when light left. By now, 7 billion years later, the merger has progressed much farther. We cannot see the current state. We watch ancient history unfold, observing a process that might have already completed. What makes this supercluster significant is its mere existence. Structures this large should be rare, edge cases in the cosmic distribution of matter. Finding them at high redshift, when the universe was younger, suggests they were more common than models predicted. Either structure formed faster than we calculated, or statistics about large-scale organization need revision. Deep field observations help resolve this question. By mapping distant superclusters and comparing their abundance to nearby ones, astronomers track how these structures evolved over time. If distant superclusters are rare, it confirms current models. If they're common, models need adjustment. Early results suggest they're not as rare as expected. Several distant superclusters have been identified, hinting at an earlier epoch of large-scale structure formation. The universe organized itself quickly at multiple scales simultaneously. Small galaxies, massive clusters, enormous superclusters all emerged in a compressed time frame. This coordinated formation points toward initial conditions. The beginning didn't create a perfectly smooth universe. Quantum fluctuations during the earliest moments seeded tiny density variations. Those variations existed at all scales, from galaxy size to supercluster sized. When gravity started amplifying them, all scales grew simultaneously. Superclusters didn't wait for galaxies to form first. They all formed together, a hierarchy of structure emerging in parallel. This means the cosmic web pattern was imprinted very early, determined by those initial quantum seeds stretched to cosmic size during the earliest moments. What we see now is the mature result of processes that began in the first fraction of a second after creation. And every supercluster carries information about those earliest moments frozen in its structure. 650 million light-years away, something massive warps the fabric of space. This concentration contains over 20 galaxy clusters, each cluster holding thousands of galaxies. Combined mass reaches levels that strain description. Gravity from this concentration influences motion across 500 million light-years of space, including our motion. The Milky Way moves through space at over 1 million miles per hour. Part of that motion comes from the initial expansion. Part comes from local gravitational influences. But a significant component comes from this massive concentration pulling us toward it. We're falling toward this structure. So is the entire local group, our collection of nearby galaxies including Andromeda. So is a larger cluster of galaxies we orbit around. Everything within several hundred million light-years feels this pull. like water spiraling toward a drain. The implications disturb comfortable assumptions about cosmic motion. We thought the universe expanded uniformly, all galaxies moving away from each other in accordance with established laws. That remains generally true at large scales, but at scales of hundreds of millions of light years, local concentrations create additional motions. Astronomers call this peculiar velocity, motion independent of expansion, caused by gravitational attraction toward nearby massive structures. Peculiar velocities complicate measurements of cosmic expansion, because you must separate expansion motion from gravitational motion to get accurate numbers. This massive concentration's influence means our measurements of expansion have built in uncertainty. When we observe distant galaxies, we measure their redshift, then calculate how fast space expands between us. But our motion toward this concentration adds to our velocity, changing the observed redshift slightly. Correct for this and expansion rates shift. Small corrections cascade into larger uncertainties. The disagreement between different measurements of expansion rate might partially result from peculiar velocities we haven't fully accounted for. If this concentration pulls us faster than calculated, or if other massive structures create motions we haven't detected, our expansion measurements could be systematically wrong. This matters for measuring dark energy. Dark energy strength determines how fast the universe expands. To measure dark energy, we measure expansion. If our expansion measurements include errors from peculiar velocities, our dark energy calculations inherit those errors. Small mistakes about this concentration's influence propagate through every cosmological parameter. But this pull affects more than just measurements. It represents something deeper about cosmic structure. Concentrations this massive should be rare in a universe where expansion wins over gravity. This concentration exists because matter concentrated unusually densely in that region, overcoming expansion's tendency to spread everything apart. Why did matter concentrate there? Trace this structure's history backward. Billions of years ago, that region contained higher than average density. Gravity pulled more matter in, increasing density further. This positive feedback created runaway concentration, snowballing into the massive structure we see today. But what caused the initial higher density? Quantum fluctuations during the earliest moments seeded variations. Some regions got slightly more matter, others slightly less. Those small differences amplified by billions of years of gravity became this concentration and other large-scale structures. Every supercluster traces back to quantum uncertainty in the first moments of existence. This concentration's future is also interesting. As the universe expands, distant regions accelerate away. Eventually, even this concentration's gravity cannot pull against accelerating expansion. Galaxies currently falling toward it will slow, stop, reverse direction. Expansion will win, carrying everything apart despite gravity's pull. This transition hasn't happened yet. For now, this concentration still pulls. Billions of years from now, that pull will weaken as expansion dominates. The concentration will become isolated, surrounded by an expanding void as other structures accelerate beyond its gravitational reach. But we'll never see that future. Billions of years from now, our own galaxy will be gone, absorbed into Andromeda during their inevitable collision. The combined galaxy will likely fall into a larger cluster, merging with other local galaxies. That larger system might eventually join this concentration, or it might be carried away by expansion first. The outcome depends on timing we cannot precisely calculate. What advanced observations revealed about this concentration comes from mapping its extent more accurately. Previous surveys estimated its mass and distance, Deep imaging detected faint galaxies on the concentration's periphery, defining its boundaries more precisely. The structure is larger and more massive than earlier estimates. This means its gravitational influence extends farther. Our peculiar velocity toward it might be greater. The corrections needed for expansion measurements might be larger. Every parameter affected by this concentration needs revision, and it's just one concentration among many that influence local motion. A concept predicted almost a century ago stated that mass bends space and light follows that bent space. Massive objects act as lenses, magnifying and distorting light from objects behind them. For decades, this remained theoretical. Then astronomers found real examples. And now, advanced telescopes use gravitational lensing as their most powerful tool. Here's how it works. A massive galaxy cluster sits between Earth and a distant galaxy. The cluster's gravity warps space around it. Light from the background galaxy travels through that warped space, following curved paths. The paths converge toward us, concentrating light that would otherwise spread out and become invisible. The result is magnification. The background galaxy appears brighter and larger than it would without the lens. Sometimes magnification reaches factors of 10, 20, even 50 times. Objects too faint to detect become visible. Details too small to resolve become clear. Advanced telescopes exploit this constantly. They target known massive clusters specifically to use them as natural magnifiers. The clusters themselves are interesting, but what lies behind them is revolutionary. Entire populations of distant galaxies become accessible only through lensing. One observation shows this dramatically. A massive cluster produces hundreds of lensed images. Background galaxies appear multiple times, stretched into arcs, smeared into streaks, distorted into strange shapes. Each arc is one distant galaxy magnified and warped by the cluster's gravity. The distortion reveals the lens's mass distribution. By mapping where light bends and by how much, astronomers reconstruct the cluster's total mass, including dark matter. Most of the lensing comes from dark matter, invisible but massive. Its gravity dominates the bending. This makes lensing one of the few ways to map dark matter directly. You cannot see dark matter. You can only infer it from gravitational effects. Lensing provides those effects in precise measurable form. The more bending, the more mass. Strong lensing produces multiple images. Weak lensing creates subtle stretching. Both reveal dark matter's presence. But lensing does more than map mass. It magnifies the faintest, most distant galaxies beyond what any telescope could detect alone. Some galaxies visible in lensed fields would require a telescope hundreds of feet across to see directly. Lensing provides that magnification for free, using gravity itself as an enormous lens. The trade-off is distortion. Lensed galaxies appear stretched, duplicated, warped. Reconstructing their true shape requires computer modeling. Astronomers measure how light bent, calculate the lens's properties, then reverse the distortion to see what the galaxy actually looks like. Sometimes one galaxy creates dozens of images. A particularly massive cluster can produce 5, 10, even 20 separate images of the same background galaxy. Each image shows the galaxy from a slightly different light path bent around different parts of the cluster. The images appear scattered across the sky, connected only by careful analysis. Finding all images from one source is detective work. Spectra help identify matches. If two arcs have identical redshift and chemical composition, they likely come from the same galaxy. Position on the sky also matters. Lensing models predict where images should appear. Finding arcs in predicted positions confirms the lens reconstruction. Advanced observations discovered something unexpected about lensing. Some of the most distant galaxies only appear in lensed fields. Without magnification, they would be completely invisible. This means our census of early galaxies is incomplete. We've only counted the brightest examples, missing entire populations too faint for direct detection. Lensing reveals this hidden majority. By targeting multiple lensing clusters and comparing results, astronomers estimate how many faint galaxies exist below detection limits. The numbers are staggering. For every galaxy we detect directly, perhaps 10 or 20 exist below the threshold, visible only through lensing. This changes cosmic census statistics. If the universe contains far more faint galaxies than we knew, total stellar mass is higher. Star formation rates need revision upward. Chemical enrichment happens faster. The universe was busier and more active at early times than direct observations suggested. Every lensed field adds to this story. Advanced telescopes have observed dozens of lensing clusters, each revealing new distant galaxies. The catalog grows weekly. Each new detection refines our understanding of when galaxies formed, how many existed, what properties they had. But lensing has limits. Only certain configurations work. The lens must be massive enough. The background object must align properly. The distance geometry must be right. Most galaxies never get lensed by anything. We only see the lucky ones where alignment happened. This selection bias affects interpretations. Lensed galaxies might not represent typical galaxies. Maybe brighter galaxies appear more often in lensed surveys. Maybe certain types align better. Correcting for these biases requires careful statistical analysis. Despite complications, lensing remains invaluable. It pushes detection limits far beyond what any telescope could achieve alone. It maps dark matter distribution. It magnifies fine details for study. This predicted phenomenon became astronomy's most powerful magnifying glass. And advanced telescopes wield that glass better than any previous instrument. A focused survey targeted a region smaller than a grain of rice, held at arm's length. What came back from that tiny patch shocked the research team. 13 galaxies, all formed within the first 500 million years after the beginning. 13 complete systems, each with stars, structure, chemical elements, all from the cosmic dawn period. Before advanced observations, astronomers knew of maybe 2 or 3 galaxies from this era. Previous instruments could detect hints, but lacked the infrared sensitivity to confirm distances. Ground telescopes saw even less. The cosmic dawn remained mostly invisible, hidden behind redshift that pushed light into wavelengths previous instruments couldn't capture effectively. Advanced infrared sensors changed that instantly. Instruments tuned precisely for high redshift detection turned cosmic dawn into an observable target. The first deep fields revealed what was always there, just invisible. Not 1 or 2 rare galaxies, but populations, clusters, collections of early structures. 13 in one small patch suggests thousands across the whole sky. Scale that up to the full celestial sphere, and the numbers become absurd. If this density holds everywhere, tens of thousands of cosmic dawn galaxies exist, each waiting for instruments to point in their direction and collect photons. This wasn't supposed to happen according to models. Theoretical frameworks predicted cosmic dawn galaxies would be rare, difficult to find. Each deep field might reveal 1, maybe 2 examples. Surveys would need to cover enormous areas to build statistically significant samples. Instead, they cluster. The 13 galaxies in this field aren't randomly scattered. They group together, suggesting gravitational clustering already operated. Even at 500 million years after creation, matter had concentrated enough for galaxies to form preferentially in overdense regions. This confirms dark matter halos formed early. Without dark matter concentrations, galaxies would scatter randomly. The clustering pattern indicates dark matter had already clumped, creating gravitational wells where ordinary matter fell and ignited stars. The cosmic web's precursor existed by cosmic dawn. Studying 13 galaxies instead of 1 or 2 changes research possibilities dramatically. With one example, you cannot determine what's typical versus exceptional. With 13, statistical analysis becomes possible. You can measure average properties, identify outliers, track variations. The 13 showed surprising diversity. Some appeared compact, densely packed with stars. Others spread across larger regions, more diffuse. Some showed active star formation, bright in infrared. Others seemed quieter, older despite their young age. The variety suggested multiple pathways to galaxy formation operated simultaneously. This complexity challenges simple models. If all galaxies formed through the same process, they should look similar at similar ages. The diversity indicates different environments, different dark matter halo masses, different gas conditions all influenced outcomes. Chemical analysis added more surprises. Several of the 13 showed oxygen in their spectra. Oxygen requires stellar processing, stars living and dying, scattering elements into space. Finding it so early means stellar generations cycled quickly. First stars formed, lived brief lives, exploded. Second-generation stars incorporated those elements, created more, died. Third generation inherited richer chemistry, all within 500 million years. The timescale barely allows for this cycling. Massive stars live just a few million years. If only massive stars existed initially, generations could cycle faster. But building detectable oxygen levels requires many generations, hundreds or thousands of stellar lifetimes. Something accelerated the process beyond current models. One possibility is star formation happened in intense bursts. Instead of steady, gradual star production, early galaxies experienced episodes of extreme activity. Millions of stars ignited simultaneously, lived together, died together. Each burst enriched the gas dramatically, enabling faster chemical evolution. Another idea suggests the initial mass function was different. Modern galaxies produce mostly small stars with a few massive ones. Early galaxies might have reversed this, producing mostly massive stars. More massive stars mean faster cycling, quicker chemical enrichment, rapid evolution through stellar generations. Both remain speculative. What the 13 galaxies definitively proved is cosmic dawn was not a sparse, rare phenomenon. It was a busy, active period with abundant galaxy formation. The universe didn't slowly wake from darkness. It exploded into light across vast regions simultaneously. The implications extend beyond just counting galaxies. If cosmic dawn was this active, reionization must have progressed faster than predicted. More galaxies mean more stars. More stars mean more ultraviolet radiation. More radiation means faster ionization of hydrogen throughout space. The fog cleared quickly. Within perhaps just 200 million years, stellar radiation ionized most hydrogen. The opaque early universe became transparent, allowing light to travel freely. This transformation enabled everything that followed, every astronomical observation we make today. Without reionization, the universe would remain dark, light-trapped, and scattered. The 13 galaxies of this survey contributed to that transformation. Their stars burned, their light spread, their radiation cleared space. Small individual contributions, but across thousands of similar galaxies, enough to change the cosmos. And we've just started cataloging them. Advanced observations captured something rare, galaxies in the act of merging. These aren't modern merger events. These collisions happened billions of years ago, light from them only now reaching us. The images freeze ancient catastrophes mid-process, galactic collisions, that took hundreds of millions of years to complete. Two systems approach each other, pulled together by mutual gravity. Initial contact is gentle. The galaxies are mostly empty space. Stars within them are so far apart that stellar collisions almost never happen. Galaxies pass through each other like clouds, interpenetrating without individual impact. But gravity doesn't pass through. Each galaxy's mass pulls on the other. Stars get deflected from their original orbits. Gas clouds collide directly. Unlike stars, when gas clouds hit, they compress, heat up, shock. Compressed gas collapses into new molecular clouds. Molecular clouds fragment and ignite stars. Merger events trigger star formation. Observations show this happening. Well, not in real time. The mergers occurred billions of years ago. But we see the star formation. Bright knots of newborn stars scattered through collision zones. Some merger systems produce stars hundreds of times faster than isolated galaxies. The collision disrupts organized structure. Spiral arms get torn apart. Disks warp and twist. Material gets ejected into long tidal tails. Streams of stars and gas pulled away from both galaxies by gravitational forces. These tails extend millions of light years, thin threads of matter stretching into space. After initial pass through, gravity pulls the systems back together. They swing around each other, interpenetrate again, separate again. Each passage sheds angular momentum through tidal forces and dynamical friction. The galaxies lose energy, spiral closer, eventually merge completely. The final product depends on the collision geometry. Head-on collisions destroy spiral structure, creating elliptical galaxies. Glancing mergers might preserve some rotation, producing lenticular galaxies. Unequal mass mergers where one galaxy is much smaller sometimes leave the larger galaxy relatively intact, while the smaller one gets shredded. Advanced observations found merger systems at all stages. Some show galaxies just beginning to interact, barely touching. Others show full interpenetration, gas clouds colliding violently. Still others show late-stage mergers, two nuclei spiraling together in the final approach before coalescence. Each stage reveals different physics. Early interactions show tidal forces at work, pulling material into streams. Mid-stage mergers show gas compression and triggered star formation. Late stages show nuclei approaching, separated by just thousands of light years, about to merge into a single massive core. When nuclei merge, supermassive black holes at galaxy centers approach each other. Each galaxy harbors a central black hole. As galaxies merge, those black holes spiral toward each other, eventually forming a binary system. The binary decays through gravitational wave emission, ultimately merging in a burst of radiation that current instruments cannot detect directly. But the aftermath is visible. Merged black holes accrete gas violently, lighting up as quasars. Advanced observations detected several merger systems showing quasar activity, evidence that black hole mergers recently occurred or are occurring. The quasar phase eventually fades as gas depletes, leaving a quiet elliptical galaxy with one massive central black hole. Merger frequency affects galaxy evolution dramatically. In dense environments like galaxy clusters, mergers happen constantly. Galaxies collide, merge, grow through accretion of neighbors. In sparse environments, galaxies evolve in isolation, rarely encountering anything to merge with. The early universe was dense everywhere. Galaxies formed closer together. Space hadn't expanded as much. Merger rates were higher, perhaps 10 or 20 times higher than today. Most early galaxies experienced multiple mergers in their first few billion years. This rapid merging explains massive elliptical formation. You cannot build a giant elliptical in isolation. You need multiple mergers combining several smaller galaxies into one large system. High merger rates in the early universe allowed this to happen quickly. Observations confirmed merger activity peaked around 10 billion years ago. At that epoch, roughly 30% of galaxies showed clear merger signatures. Today, the rate drops to maybe 5%. The universe has calmed. Space expanded enough that galaxies sit farther apart, reducing encounter frequency. But mergers still happen. Andromeda and the Milky Way will collide in about 4 billion years. The merger will take billions of years to complete, reshaping both galaxies into a single elliptical system. Observers on planets in that future galaxy will see a very different night sky. Watching ancient mergers through advanced telescopes gives us preview of our own future. The processes we observe in distant galaxy collisions will happen locally. Gas clouds will compress and ignite. Star formation will spike. Tidal forces will create streams. Eventually, two nuclei will spiral together. Two black holes will merge. The collision is inevitable, already in motion. Andromeda approaches at about 70 miles per second. Nothing can stop it. Gravity guarantees the collision. We watch distant examples to understand what awaits us. Yet despite violence on galactic scales, individual stars remain safe. The vast emptiness of space protects them even during direct collision. Stars pass through gaps between other stars. Planets survive. Life could persist through merger events, watching the sky transform but experiencing no direct catastrophe. The real danger comes from the central black hole merger. Gravitational waves and jets from the merged black hole could sterilize regions near the galactic core, but most stars orbit far from the center, safe from direct effects. The merger reshapes the galaxy without destroying most stellar systems, and billions of years later, a new stable configuration emerges. Two numbers refuse to agree. The expansion rate of the universe can be measured two ways. Each method is precise, well-tested, verified by independent teams. Both should give the same answer. They don't. Measure expansion by looking at ancient radiation from early in the universe's history. This ancient light from 380,000 years after the beginning encodes information about cosmic properties. Tiny temperature variations map density fluctuations that later grew into galaxies. By analyzing these variations, cosmologists calculate how fast space expands. The answer is about 67 kilometers per second per megaparsec. This means for every megaparsec of distance, roughly 3.3 million light years, space expands at 67 kilometers per second. Double the distance, double the expansion speed. It's a clean, consistent relationship. Now measure expansion differently. Look at nearby galaxies with known distances. Measure their redshift to see how fast they recede. Divide recession speed by distance. This gives expansion rate directly from local observations. The answer is about 73 kilometers per second per megaparsec. 6 kilometers per second difference. That sounds small. It's not. The measurements are precise to within 1%. A 6-unit difference is highly significant statistically. One or both measurements must be wrong, or something is missing from our understanding. Astronomers call this the expansion rate tension. Advanced observations were supposed to help resolve it. New instruments can measure distances to faraway galaxies more precisely than previous instruments. Better distances mean better expansion calculations. Everyone expected new observations to clarify which measurement was correct. Instead, they made the tension worse. New distance measurements confirmed the higher expansion rate of 73 kilometers per second per megaparsec. This strengthened the local measurement, making the discrepancy with early universe measurements even harder to explain. Something is genuinely wrong. Either our understanding of the early universe is incomplete, or our local distance measurements have systematic errors, or the expansion rate actually varies across cosmic time in unexpected ways. One possibility is dark energy behaves differently than assumed. Standard cosmology treats dark energy as constant, pushing space apart at a steady rate. If dark energy's strength varied over billions of years, early universe measurements and late universe measurements could give different answers without either being wrong. This requires modifying fundamental theories. Current equations allow for changing dark energy, but most versions create other problems. They predict cosmic structures that don't exist or expansion histories that conflict with other observations. Making dark energy vary just right to fix the tension, without breaking everything else, is extremely difficult. Another idea suggests the early universe contained extra radiation. More radiation in the early cosmos would change calculations, shifting the predicted expansion rate. If some unknown particle or field contributed radiation energy, it could reconcile the measurements. But this requires inventing new physics. No particle in the standard model provides the needed radiation. Any solution requires something beyond current theory. Scientists prefer fixing problems with known physics before adding new particles. A third option suggests distance measurements have hidden errors. The local expansion measurement depends on a ladder of distances. First, measure distances to nearby stars using parallax. Second, calibrate standard candles like variable stars. Third, use those variables to calibrate supernovae. Fourth, use supernovae to measure distances to distant galaxies. Each step introduces potential error. If variable star calibration is wrong, everything built on it collapses. If supernovae aren't as standard as believed, distances calculated from them are unreliable. Small errors in early ladder rungs get magnified at later rungs. Advanced observations tested the ladder carefully. Instruments observed variable stars in distant galaxies, measuring their properties more precisely than previous instruments could. The results confirmed variable star calibrations are solid. This eliminates one possible error source, but deepens the mystery. The tension now sits at statistical significance exceeding 5 sigma. In particle physics, 5 sigma means discovery. The effect is real, not a statistical fluke. Applying the same standard to expansion rate tension suggests the discrepancy is genuine, requiring explanation beyond measurement error. What terrifies cosmologists is the implication. If the tension is real, our standard cosmological model is wrong. Not slightly inaccurate, fundamentally wrong. The model that explains early radiation observations, galaxy distributions, large-scale structure, everything fails to explain expansion rate measurements. This would require rewriting cosmology, not tweaking parameters, not adjusting assumptions, potentially replacing the entire framework with something new. Decades of careful model building would need revision. Alternative explanations exist but seem unlikely. Maybe we live in a cosmic void, a region with lower than average density. Expansion might behave differently in voids. This could create local measurements that don't match global average. But we see no evidence for such a void. Surveys map matter distribution around us. The data show we live in a fairly typical region, not a significant under-density. The void explanation requires a void we haven't detected. Or maybe gravity behaves differently than general relativity predicts. Modified gravity theories exist. Most fail to match observations. A few survive scrutiny, but require fine-tuning that feels contrived. They solve the expansion tension by creating other problems. The cleanest solution would be finding a hidden systematic error, some subtle mistake in how we measure distances or interpret redshifts. An error that multiple independent teams all made the same way. possible but increasingly unlikely as checks multiply. Advanced observations continue collecting data. Each new measurement either narrows the tension or confirms it. So far, confirmation dominates. The expansion rate discrepancy holds across different methods, different distance indicators, different samples. The universe is telling us something important. Empty space pushes everything apart. This sounds impossible. Emptiness cannot push. But quantum field theory predicts that vacuum itself contains energy. That energy has pressure. Negative pressure. Instead of pulling things together like normal pressure, negative pressure pushes them apart. This is dark energy. We cannot see it directly. We infer its existence from cosmic acceleration. The universe doesn't just expand, the expansion speeds up. Galaxies recede faster now than they did billions of years ago. Something pushes against gravity, overwhelming attraction with repulsion. Measurements show dark energy constitutes 70% of the universe's total energy density. Matter, both ordinary and dark, comprises the other 30%. This means most of the universe consists of something we don't understand, something that behaves oppositely to everything else. The acceleration was discovered in the late 1990s. Two teams independently measured distances to distant supernovae. They expected to find deceleration from gravity slowing expansion. Instead, distant supernovae appeared farther away than predicted. The universe was accelerating. The discovery won a Nobel Prize. It also shattered comfortable assumptions. Before, cosmologists worried about whether expansion would slow enough to reverse, causing eventual collapse. Acceleration eliminated that possibility. Expansion will continue forever, accelerating perpetually. Advanced observations refined measurements of acceleration strength. By observing distant galaxies at multiple redshifts, astronomers map how expansion rate changed over time. The data reveal dark energy's influence grew as the universe aged. Early on, matter dominated. Gravity slowed expansion. Then dark energy took over, reversing deceleration into acceleration. The transition happened about 6 billion years ago. Before then, expansion was slowing. After, it was speeding up. We live in an accelerating epoch, watching distant galaxies race away faster every moment. Dark energy's properties remain mysterious. Is it truly constant vacuum energy, unchanging forever? Or does it evolve, growing stronger or weaker with time? The simplest assumption is constant dark energy fits most observations. But small deviations might exist, detectable only with extremely precise measurements. Every astronomical observation we make today exists because of processes that occurred billions of years ago, captured in light that has traveled unimaginable distances to reach us. The universe reveals itself through this ancient light, showing us not just where we are, but where we've been, and hinting at where we're going in the vast cosmic journey that continues to unfold.